Okay, I'm here to talk about electric fields. Now, just as we've talked about objects with mass create a gravitational field around them that affects other objects with mass nearby, and there's other fields we've talked about too. There's also electric fields, meaning that if you have a charged object, it will create a field around it. And other charged objects that are in that field will be affected by that field. So they will feel a force of some sort. So we often will use vectors to describe the electric field, and the field lines that we draw point away from positives and towards negatives. So we're going to show you what that looks like. And if you think about it, we often think about this in terms of test charges. So we can put like a little test charge, and that's something that we're going to test out and see what happens to it. And that test charge is going to feel a force because it's an electric field. It's got a charge. It's typically a positively charged test particle. And the vectors that we're going to see show the direction of the force on that positively charged test particle. So it's a positively charged particle. There's an equation to go with this too. E equals F over Q, where F is force and Q is charge. We've seen those letters before too. And the units for this are newtons divided by coulombs. So force is in newtons, charge is in coulombs, newtons per coulomb. We can also rewrite this equation. This is the one that you see on the reference table. But we've seen that force is equal to K Q1 Q2 over R squared, right? So, and that's divided by Q. And the question becomes, what is this Q compared to those Qs? Well, this tells you the force between any two objects. This tells you the charge of the test charge right here, right? So of these, you got to figure that one of them is going to be the test charge. We'll say Q2 is the test charge. And Q1 might be a charged object. So if you do it this way, one of these Q's is the same as that Q. So they cancel each other out. And you get force divided by charge is K Q1 over R squared. So force divided by charge. And what we find is that the field depends not on the test charge itself, but it depends on the main object that we were trying to test. And that kind of makes sense because this is very similar to G, which we talk about as the acceleration due to gravity, but is also known as the gravitational field constant, or gravitational field strength, very similar to the electric field strength, meaning if you have your equation F equals G M1 M2 over R squared, and gravitational field strength G is equal to F over M. F equals mg comes out of this, right? 1 over m2, both of those go away. That's g m1 over r squared. And what we find is that g, the acceleration due to gravity, does not depend on the mass of the object. All objects on Earth fall at the same acceleration. Everything has an acceleration of negative 9.8 meters per second squared on the surface of the Earth. Doesn't matter if it's big or small, as long as you ignore air resistance. Well, the same is true for electric field strength. All those test particles would have the same, what would be electric field strength, regardless of what their individual charges. So KQ1 over R squared. So let's imagine, for example, we have a positively charged object. And we were to put a test charge here. You could measure the force on this, and that force divided by the charge on the test charge gets you the gravitational, or the electric field strength. We know that positive, so field lines point away from positive and towards negative, but if this is a positive charge, we know that it's going to feel a repulsive force anyway, so we know that the line has to go away from the positive charge. We could move the test charge over here and repeat the process, and there, and repeat the process. And what you end up getting, eventually, is an electric field that looks like this. And wherever you measure the electric field strength with your test particle, you find that no matter what test particle you use, the electric field strength is the same. The force might not be the same, because the force is going to depend on the actual charge of the test particle, but the field strength will be the same. So a negatively charged one is going to look very, very similar. The negatively charged one, the only difference is going to be that instead of pointing away, your test particle is attracted to it. And your test particle is positive, right? So those field lines are always going to point inward. You could have something like this, where you have a positive and a negative. And a positive, again, the lines point away from it, and they point towards negative. You end up getting curvatures in here. Positives go away, negatives go towards. What are we drawing out of? What if you end up getting something that is two positives? By the way, if you need to rewind that and write that down, please do so. Positive. So we know that lines point away from positive. But the question is, what if they point towards each other? Well, you see curvatures. So they're pointing away. If you put your test particle here, those field lines show you what the force is on the test particle if your test particle is positive. So right here, your test particle is going to feel a force that is upward. If you put a negative test particle in here, you've got to know that the opposite force is going to be true. So your negative particle, if you put your electron up here, it's going to feel a force. If it was positive, it would feel an upward force. Negative is going to feel a downward force. And that's one way to figure out what direction the force is, because you could also just add vectors. You'd have a vector there and a vector there, both of which point up for positive charge and point down for negative charge. So you can figure out what the actual vectors would be. If we take two negatives instead, negative, negative, looks a lot like the last one. So I'm point towards it. So you put your positive test charge here, and you follow the field lines, the positive test charge feels a downward force. And if you just think of this in terms of vectors, if you've got a positive charge here, and a negative there, and a negative there, well, this one is attracted to that one, but it's also attracted to this one. If you use vector addition, the tip-to-tail method, you can combine these. You do like the complete the parallelogram, and you draw your resultant, which I'm going to do in purple, maybe like this. That's your resultant. So your resulting force is downward, just like we see here from the field lines. This is it. There's one special case I want to talk about briefly, though, which is parallel plates. So with parallel plates, we'll see a few different instances. Parallel plates, aka capacitors. You might have a positive side and a negative side. And so what we see is that the field lines tend to go positive to negative straight down like this. You do it around the edges, sometimes get a little bit of curling, but inside the lines they should go straight down. Let's say you put, aka They're often called capacitors. And we'll talk a little bit about them. In test problems, they tend to be called parallel plates like that. So let's say you put your test particle in here someplace. That's your test particle. And it should feel a force that is, let's see, it's repelled. We're going to say that's a positive test particle. This would all be reversed if you had a negative test particle. But if it's a positive test particle, it's going to be repelled by the top, and it's going to be attracted to the bottom, so it's going to feel a force downward. So if you shoot, for example, because they like to do questions on the regions like this, negative, 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 negative. Let's shoot a proton through here and see what happens. Well, it goes through here, and it goes through the plates. It feels a repulsive force from the top and an attractive force to the bottom. So as it goes through, it will curve down. If you did the same thing with an electron, you shot it through here, the electron would feel an attractive force towards the top, a repulsive force from the bottom, and your electron would shoot up here. So your electron is going to go up, the proton is going to go down. The one last thing that you occasionally see crop up is the force on it. So imagine this. We got a particle here at point A. We got a particle here. You know, I'm going to make those in blue to separate them a little bit. A, B, and C. And let's just keep them positive for now, but it doesn't really matter. You get the same result. So A has got a strong attractive force because it's close to the negative, right? But it's got a weak repulsive force. C, which is close to the top, has got a strong repulsive force and a weak attractive force. B has got a little bit of both. So what we find is that the further down you get, the stronger the attractive force, but the weaker the repulsive force. And since the resultant is really the combination of the two, turns out that no matter where you go, at all locations in here, the force is the same. How much of it is attractive versus how much is repulsive changes. But at all locations between the parallel plates, the forces are equal. And this has some nice consequences. So if you send any particle in here, you'll know that you'll know consistently what its force is going to be, because no matter where you put it, the force is going to be the same. Once we start talking about voltage and voltage difference, we'll see that in parallel plates, the voltage changes, but the force is the same in all places. I think that about does it for this video. Thank you very much for watching.